Welcome back to our Chem 152 video series. In this video, we'll talk about how to compare acid and base strength. The first problem gives us HN3, which is a weak acid, and a Ka value of 1.9 E-5. You can think of the Ka value as a representation of how strong the acid is. A higher Ka represents a stronger acid. The question asks us to find the conjugate base and the Kb of the conjugate base. In order to find the conjugate base of a weak acid, we react the weak acid with water and allow the weak acid to give up a hydrogen. Let's try that with our acid. We'll begin with HN3 reacting with water. Because HN3 is a weak acid, water will act as a base here. Our weak acid will lose a hydrogen, and it will go negative. This will give us N3 negative as our conjugate base. Our base, on the other hand, will gain an H and go positive. Therefore, our base, rather than being H2O, will be H3O, positive, and this is our conjugate acid. Now we know the identity of the conjugate base. Now we can find the Kb for that conjugate base with a little bit of algebra. The Kb of that conjugate will equal K water divided by Ka of the original acid. In this course, we can say that K water is 1 times 10 to the negative 14th power, and our Ka was 1.9 times 10 to the negative 5th. If we divide, this will give us the Kb of our N3, our conjugate base. We end up with a Kb of 5.26 times 10 to the negative 10th power. Notice that this is quite a bit weaker than our acid. This means our conjugate base that we ended up with is a fairly weak base, quite a bit weaker than how strong the acid was. We can do the same process for weak bases. In this question we have NH3 and we are told it's a weak base with a Kb of 1.8 times 10 to the negative 5. We can find its conjugate acid by reacting it with water as well. We know NH3 is a base, therefore water must act as an acid in this problem. Our base will take H and go more positive. Therefore the NH3 becomes NH4 with one additional hydrogen, and it will be positive. This is our conjugate acid. Water, acting as an acid, will lose an H and go more negative, giving us OH negative. This will be our conjugate base. So now we know what the conjugate acid is. We can say that the Ka of a conjugate acid is equal to K water divided by Kb of the original base. We can take K water again to be 1 times 10 to the negative 14th power, and Kb to be 1.8 times 10 to the negative 5th. If we divide this, we'll get 5.56 times 10 to the negative 10th power. Once again, notice that the strength of the conjugate acid is quite a bit weaker than our original base. Let's collect what we've calculated here on this page. We were given that the NH3's acid strength, Ka, was 1.9 times 10 to the negative 5th. Based on that, we found that the Kb of its conjugate base was 5.26 times 10 to the negative 10. We were also given that NH3, a weak base, had a Kb of 1.8 E-5, and we found, using our math, that our Ka of the conjugate acid, NH4 positive, was 5.56 times 10 to the negative 10. So now we're asked which is the stronger acid based on the Ka values that we have in front of us. Now remember, the higher the Ka is, the stronger of an acid you have. So if we examine these values, 1.9 times 10 to the negative fifth and 5.56 times 10 to the negative 10, we can see that 1.9 times 10 to the negative fifth is definitely stronger because that's higher than anything raised to the negative 10. Just like for acids, a higher Kb represents a stronger base. If we examine our numbers, 1.8 times 10 to the negative fifth is definitely higher than 5.26 times 10 to the negative 10, meaning that NH3 will be our stronger base. The important thing is here, we could not have compared acid strength or base strength for either of these unless we had done the math and found the Ka and Kb of the conjugates. You may run into cases where you have to compare acids but don't know what their Kas are. So there are some general guidelines to work with if you have no values for Ka to look up. The first case is if you have two similar looking acids but they have different numbers of oxygen, such as this first question where we have HClO2 and HClO4. All other things being equal, if you have more O's in the acid, you have a stronger acid. This comparison only works if you have similar acids, such as these two, which start with HCl and then a number of oxygens, though. So be careful about misapplying this rule where you can't use it. You can only use it for similar acids. However, in this case it will work because we do have two similar acids, and we can see that HClO4 has more oxygen. Therefore, HClO4 is stronger. Now, for simple binary acids, which just have hydrogen directly connected to one central atom, there's a different trend that we look at. For these binary acids, which just have hydrogen and a central atom, generally the acid will be stronger if the central atom is more electronegative and larger. If you are electronegative and large, this will make you a stronger acid. If you're not sure, it may help you to look up the central atoms on the periodic table. Here we have oxygen and chlorine. Now chlorine is in row 3 on the periodic table, and oxygen is row 2. Row 3 elements tend to be larger. Both of these factors will make HCl a stronger acid than water. If you actually look up this information, you'll find that HCl is indeed a strong acid, and water is a very weak acid. For our third question, we have another example with H2SO4 and HSO4, two very similar acids that only differ in the number of hydrogen. If the only thing that differs is the number of hydrogen, more hydrogen makes you a stronger acid. Based on that, we can say that H2SO4 will definitely be stronger than HSO4 because it has 2 hydrogen as opposed to HSO4's 1 hydrogen. If you look these up, H2SO4 will be a very strong acid. HSO4 will be one of our weak acids. Most of the principles that apply to acids will also apply to bases, except for in reverse. Here we have a scenario where we have 2 similar bases, but all they differ in is the number of oxygens. With regard to the number of oxygens, more oxygens typically makes you a weaker base, and less oxygens makes you stronger. This is exactly the opposite of the way acids worked. If we compare these two bases, ClO4 has more oxygen, therefore it will be a weaker base. ClO2 negative has less oxygen, therefore it will be a stronger base. For binary bases, such as NH2 negative or OH negative, again we look to electronegativity and size. For bases, a stronger base will be a smaller atom that is less electronegative. When we look to our binary bases here, NH2 negative and OH negative, both have central atoms that are on row 2 because nitrogen and oxygen are both row 2 elements. They'll be fairly similar in size, however, nitrogen is less electronegative. Therefore, NH2 will be our stronger base. In fact, if you look this up, NH2 and OH are both very strong bases, but NH2 is a good bit stronger still. Again, this rule is exactly the opposite of what we saw for acids. For our third example, the only thing that differs between HPO4 negative and PO4 negative is the number of hydrogens. For bases, having no hydrogen tends to make you a stronger base, and having more hydrogen makes you a weaker base. The only difference between these two bases is that one of them has a hydrogen and the other one does not. And the one that does not have hydrogen will be our stronger base. So even if we don't have Ka and Kb values, we can still sometimes make comparisons between similar acids or similar bases based on the number of hydrogen, the number of oxygen, and what the central atom is, and how electronegative the central atom is. Thank you for watching. We'll see you again soon.